Alright guys, so we're gonna solve the midterm solution right now. So this is our midterm, and I'm gonna start by solving this first problem basically, where we had a wheel and you had a person sitting over here and the angle was equal to 45 degrees and the wheel was rotating in this direction at omega is equal to 3 revolution per minute. So revolution per minute is usually referred to as 3 rpm. So the velocity of this guy is actually like that, right? And we had a car over here. Okay, fair enough. All right, so this is a car, and the car was traveling with a velocity of 18 kilometers per hour, right? So VA was equal to 18 kilometers per hour. All right, and then this is the observer at B, and the goal was we are trying to find the velocity of A with respect to B. So we always know that the velocity of A as a vector is equal to velocity of B plus any relative velocity that we have between them, right? So VA is always equal to VB plus VA with respect to B. So VA with respect to B is equal to VA minus VB. Now, for me to be able to make this a subtraction, basically, I need those two vectors to be expressed in the same coordinate frame. I cannot, for example, express VA in some frame and then VB in a frame that rotates with that and say this is what they are. So I have to have the same frame, right? And then compare like basically apples to apples, right? So this is my IJ frame, and then this is what I would need here. Well, I know VA is going to be equal to 18 kilometers per hour, and then this is along I. So 18 times 10 to the 3 divided by 1 hour, which is equal to 3600 seconds, and then that is going to be in meters per second. If you do this, I think you will end up with 5 meters per second. So this is your VA. Now what remains to have is the velocity of B. So the velocity of B is going to be equal to, now in this case we can use the polar coordinates, and then it will be equal to r prime UR plus r theta prime U theta. And now theta is going to be in the direction of the rotation, so this velocity is going to be downward, right? What is r prime? R prime is going to be 0. R prime is the rate of change of the radius of the Ferris wheel, right? And then that is not changing, right? Because the radius is not increasing. All right, so we only end up with r theta prime. What is r? R is equal to how much? 9 meters. So 9 times theta prime, but theta prime has to be in radian per second. So 3 revolutions per minute is equal to how many radians per second? So how many radians are 3 revolutions? So 3 times 2 pi, right? So every revolution is 2 pi divided by a minute, which is 60. So this is going to be in along U theta, and then that velocity is in meter per second. So basically you are finding the velocity of this point coming downward, right? You're finding this velocity coming downward. So we have to essentially do this multiplication, and if you do this, I think you will end up with 2.82 U theta meter per second. Now what remains is we need to find U theta. How do you calculate U theta? So U theta is a vector that is basically 45 degrees. So we have a 45 degree like this, right? And then this vector is coming downward like that, right? So we know this angle is going to be here 45 degrees, right? So it's going to be 45 in the I direction, like cosine 45 in the I direction, and then minus sine 45 in the I direction. So that would be 2.82, and then we know cosine 45 is equal to sine 45. So square root of 2 over 2 I minus square root of 2 over 2 J, right? And if you do this computation, you are going to end up with 2. So 2 I minus 2J. Okay, so this is what I mentioned. So the angle is going to be 45 between this angle and this Ferris wheel, right? At this 45 degree, right? And we it will be cosine 45 in the I direction, and then sine 45 in the minus J direction. And we know cosine 45 is equal to sine 45 is equal to square root of 2 over 2. Now what remains is we just need to find VA minus VB. So VA with respect to B is equal to how much? VA minus VB, right? Which is equal to, what was VA? VA was equal to 5, right? So 5I minus 2I minus 2J. That would be equal to 3I plus 2J. Alright guys, and that would be this answer, 3I plus 2J. Okay, so you can see it's basically like a 5-minute problem, pretty basic stuff. Okay, next problem is the amusement park, basically, where we had this guy was essentially rotating, right? And then we had people suspended on that, and then we had this guy, and then we knew we were trying to find what is the constant velocity of the passengers on the amusement park. Basically, we're trying to find this, velocity, right, in this plane, in the horizontal plane, right? This guy is fixed over here. It's rotating up like that, and this is your vertical line. Essentially, that means G is downward, right? And then this is the passenger, and we would like to find what is the constant velocity of this, so that the supporting cables make an angle of 30 degrees. All right, so how would you do this? I think that would be very basic, right? If you drove this free body diagram over here, so this is going to be your line, right? This is my angle theta, which is 30 degree. I have the weight mg, and I have the tension. Do I have anything else over here? Probably not. We don't have any acceleration in the forward direction, so that's it. So we're gonna have this mv squared over r, right? Is gonna be our normal. This is our normal acceleration, or this is our normal inertial force, right? So if this angle is theta, then this angle right there is theta. And if I sum the forces in this direction, right, I'm going to get what? T sine theta, right, or minus T sine theta, because of summing the forces in this horizontal direction. I'm going to get minus T sine theta, right? How about on the accelerations? I'm also going to get minus mv squared over r, right? So T sine theta is equal to mv squared over r, and what I need to know here is what? Do I know the tension? I don't know the tension. So to find the tension, I'm gonna have to sum the forces in the upward direction. All right, and that would be T cosine theta minus mg is equal to 0, right? So T is gonna be equal to mg over cosine theta. So I'm gonna take this T and then I'm gonna put it here. So I'm gonna end up with, so this is equation 1 and 2. So I'm gonna say 1 and 2. That would give me what? Mg, right? Mg, so Mg over cosine, Mg tangent theta is equal to V squared over R. So M and M will actually cancel out. So V is gonna be equal to what? Square root of R G tangent theta, right? If you do the calculations of that, we're gonna end up with what? What is your radius in this case? The radius is gonna be equal to how much? 4 meters, right? So we have 4 meters, and the length of this is actually 6 meters. So we have from here to here we have 4, and the length of the cable is 6. So basically, remember, this is the whole radius, right? So it will be equal to 4, right, plus 6 sine of the angle, right? 4 plus 6 sine of 30 multiplied by 9.8 multiplied by tangent 30. Okay, if you do this computation, basically you're going to end up with 6.293, which is equivalent to 6.3 meters per second, which was available in the answers. All right, so that is it for this problem. Second portion of this problem was to find the tension, and the tension is simply mg over cosine theta from the free body diagram. 50 times 9.8 divided by cosine of 30, and this number is going to be equal to 565. 565.8 Newton, and then that was also available in your solution. So the tension, why is it equal to mg over cosine theta? Because the tension that is applied on this problem basically is, or on the chair basically, is equal to the tension in the cable, right? So the person is connected to the amusement park by the chair, and the chair is connected to the amusement park by the cable, so it would be equal and opposite force, and then that would be basically equal to T. And this is from this free body diagram, right? So this is the force that you're looking for. All right, next is the pendulum problem, and the pendulum problem basically is we have a bus, right? And the bus is carrying this pendulum problem, right? So this is a platform, right? And then we said we have a student who has like some pendulum experiment, you know, for dynamics course or for like physics class or whatever. And the guy notices that when the bike tries to accelerate, this guy basically makes an angle, and this angle is theta, right? If you zoom in on here, basically the student sitting on a bus notices that the pendulum makes an angle of 10 degrees, right? So how do we know the bus acceleration from this experiment? So all that you really know, you don't even know the mass here. You simply know that when the bus accelerates, you are looking at the angle 10. You find the angle 10. So how do you relate the angle that a pendulum makes with the acceleration of the platform, right, or the bus? How do we address this problem? We have to do a free body diagram, right? So a free body diagram on here would look like you have T, you are going to have mg. If this angle is 10, then we know this angle is going to be 10. And how about on this end? On this end, you're going to have ma, right? Ma is a inertial force applied on the pendulum, right? As a result of the platform acceleration, automatically everything on the bus will actually have this ma, including this object, right? Now, how do we actually get a? So we have to sum the forces in x direction. We're going to get t times sine theta. I'm going to keep 10 as theta. T sine theta is going to be equal to ma, but I don't know t. How do I do that? Then I'm going to sum the forces in the vertical direction. Then I'm going to get t cosine theta minus mg is equal to 0. So now notice that t is going to be a function of m, and when I put t as a function of m here, m will cancel out. Therefore, I'm going to be able to actually get theta. So t is going to be equal to mg over cosine theta. So putting this over here, I'm going to end up with mg sine theta over cosine theta, which is equal to tangent theta, is equal to ma. So m and m will actually cancel out. So a is going to be equal to g tangent theta. So the acceleration is actually simply related to the angle that the line will make, or a pendulum will make, if you are sitting on a platform. So a is equal to how much? G, which is 9.8 times tangent of 10 degrees, right? Let's do this. If you do this, it will be basically equal to how much? 1.72. 1.72 meter per second square, which was available for you. All right, pretty basic, guys. Okay, so that is for this problem. Okay, guys, so this is the last problem basically, where we had a car, and the car was going on a ramp. We had the gravity was going downward, and the car was basically rotating around this axis of rotation along this ramp. So the car is actually traveling like this, traveling like that, and then coming back like that. Alright, the radius of curvature is equal to 100 meters. The weight of the car is equal to 1700 kilograms. So these are the tires of the car, right? So these are the two tires, and then the other two tires are actually behind these, right? So the car is going into the paper and rotating. We're trying to find what how much can this car speed up on this ramp before it actually starts. You can imagine that when the car speeds up, basically ultimately it's going to start to, you know, skid down. Maybe it's going to like rotate like that and then fall, right? Okay, so we need to find that maximum velocity. So how do we calculate that maximum velocity? We have to do a free body diagram. The free body diagram, well, we know mg is going to be vertical downward, normal force is going to be downward like that, right, perpendicular to the surface or perpendicular to the tires, which is in that direction. And then the friction force will be opposing the motion, the sliding motion of the car, which is equal to mu s times n. The reason why I have friction as mu s times n is because that would be the maximum friction force that is developed between the tires and the surface of the pavement or the road. So these are all the external forces which are applied on the car. We still have our inertial forces. So the only acceleration that we have is a centrifugal acceleration, because the velocity vector of the car is changing direction continuously, and you know mv squared over r is going to be pointing toward the center of rotation, right? Okay, so we need to know we need to solve for the velocity. How many unknowns do you have? So we have n, right? So we need to be able to get n, and we can technically get n by, how can we get n? We could technically get n by summing the forces in the upward direction, right? If this angle is theta, right, then what is that angle? Then I think this angle also will be, right, so this guy is perpendicular to this. If that angle is, yeah, so one way to, you know, not having to solve for mv squared over r directly, we can try to sum the forces in a vertical direction, right? And then if you try to sum the forces in a vertical direction, if well, this angle is theta, then we know this angle has to be equal to theta, right? Why? Because if this guy is 0, so summing the force in the vertical direction, I'm gonna get what? N cosine theta minus n cosine theta minus mg. How about the frictional force? So that friction force will actually also be having a contribution, which will be basically, well, this angle is theta, then that would be minus mu s n times sine theta, and that would be equal to 0, right? So summing the forces in the vertical direction, I'm going to get n cosine theta minus mg, and this is your frictional force, right? Frictional force is, it has this contribution, right, which is f us multiplied by how much? A sine of this angle, right? That angle is theta, right? So this force times sine theta will gonna give me this contribution, right? So minus sine theta. So this is a quick shortcut for me to be able to find n, because I don't want to include mv squared because my velocity is a variable. I could definitely sum the forces along this direction, but if I do that, then I'm gonna have to incorporate mv squared over r, and basically I'm adding this variable multiple times. So this is a quick shortcut for doing that. So n cosine theta minus mu s sine theta is gonna be equal to mg, right? So basically now I quickly find my normal and now what else? So I got my normal force, right, by simply looking in the force diagram. Now if I were to get my velocity square, right, what is the easiest way of getting this mv squared over r? So basically I could try and sum the forces in that direction. So if I sum the forces in that direction, what do I get? I'm gonna get on this end, I'm gonna get mu s n, right, cosine theta, right? So this is your friction force. The weight isn't doing anything because it's perpendicular to the motion. And by the way, this is the beauty of dynamics. It doesn't really matter which axis you use. The equation F is equal to ma actually applies in any direction, applies along this direction, that direction, that direction. In any direction that you sum the forces, they would actually be equal to mass times acceleration. Right? If you sum the force in a vertical direction, you have no acceleration because that thing is basically stationary at that instant. Okay, summing the forces in the horizontal direction, I'm going to get mu s times n, right, times cosine theta. Why? Because we know this angle, or this is a friction force, so mu s, so friction force times cosine theta. How about n? N is also equal minus n times sine theta, right? This angle is theta as well, right? So n times sine theta, and that is equal to how much? Mv squared over r. So solving for the velocity, right? So v squared is equal to r over m, right, multiplied by n multiplied by mu s cosine theta minus sine theta, right? So that is equal to v squared is equal to r over m us cosine theta minus sine theta multiplied by n, which is equal to how much? M times g divided by cosine theta minus us sine theta. So m and m will cancel out, so the velocity is going to be equal to the square root of this whole thing, right? I'm going to rewrite it one more time. So the velocity is going to be equal to the square root of r times g times mu s cosine theta minus sine theta divided by okay, by the way, think when I sum the forces in horizontal direction, this guy has to be minus, so minus mv squared over r, right? Minus mv squared over r, so this whole thing is minus, so plus here, and then I have to add actually minus over here. Okay, so this will basically just change the sign that I have here. So this guy is minus, and then this guy is plus. Okay guys, if you do this problem, if you do this analysis, basically this is computation, you will see that the velocity is equal to 12.4, which was available in the multiple choice. Some reason Blackboard actually didn't take this as a positive number, as a correct number. So I'm going to update that on Blackboard. I think Blackboard used 24.4. So I'm going to update that, and when I update that, automatically your grade will actually be updated based on that. Okay, now going into the multiple, the true and false problems. Basically what we had is the first one, a point mass can have zero acceleration, zero velocity, yet it's still moving. Obviously that is false. It is possible that the net force on a particle is greater than zero, but the particle's acceleration is zero. So it is impossible, obviously, that you have total, if you have total forces in one direction, then we have to have ma, right? It cannot be possible that you have a positive force and zero acceleration, right? So if you have a force, then you must have ma, where a would be equal to f over m. Okay, this is the second problem. Total force on a particle is zero. The particle can still be increasing. Obviously this is false. A point mass moving along a curve with a constant velocity will have zero acceleration. Of course not, because you could be moving in a constant velocity along this path, but because your velocity vector is changing direction, and we know a is actually equal to dv over dt as a vector, not just as a magnitude, then it will be zero, right? Then you would have an acceleration because the velocity vector is changing direction, and we have been referring to this acceleration as the centrifugal or v squared over r. Two projectiles with different masses, m1 and m2, where m2 is greater than m1, will travel, one of them will travel larger distance if m1, for example, is greater or smaller. No. Why? Because nowhere in the equation of the projectile, basically the mass, you will actually have the mass, right? Not in the range, not the displacement, nothing, right? So the path of the projectile, living in a perfect world, will actually always be equal, right? It's independent of the mass. In a curvilinear motion, direction of normal acceleration can point inside or outside the circle, so that is it. So no, right? It always have to point toward the center of curvature, right? It can never point in the opposite direction as the center of the curvature. All right. Now next problem: external force. The external resultant force must be in the same direction as the motion. Is that true? No. Why? Because the external force has to be in the same direction as the acceleration, right? So, for example, your car could be sliding downward, but you're applying the brake. Your acceleration is positive, but you are moving in the opposite direction, right? Guys, motion is associated with velocity, right? And the force by no means has to be in the same direction as the velocity. You could be traveling at 100 kilometers or 200 kilometers per hour. You're trying to apply the brake, right? Your force is backward, right? Net force is backward, but you are still moving because you had an initial velocity. External force must be in the same direction as the acceleration, yes. Velocity graph is horizontal line, the particle is staying at rest, yes, because the velocity is not changing. The VT graph is linear descending, the acceleration of the particle is decreasing. So I've actually had some questions on that. So this is your VT graph, right? This is your time, this is your velocity, and then if the VT graph is downward, then the acceleration is equal to a dv over dt, which is basically the slope of this angle, which is below that, right? So here basically I'm willing to actually say that, so the acceleration of the particle is decreasing. So here what I really meant is that the acceleration is negative, right? Negative acceleration basically meaning that sort of like, you know, the velocity is decreasing, not the actual acceleration is decreasing. So here basically this is false, right? So I'm going to update that to reflect that change, okay? So this problem, in this case, basically the acceleration is negative, right? But you know, decreasing here, you know, is the acceleration itself would have to be decreasing. So this is going to be false because the acceleration is constant, is the slope of this angle. All right, so I'm gonna update that as well. If a particle is moving in a circle at a constant speed, the acceleration of the particle is 0. No, right? We've already described that. Okay, guys, so that really sums up the solution. And now we're going to continue with a new chapter with kinematics, and this is a very important chapter that we're dealing with right now, which is basically the heart of dynamics. We need to be looking at rigid body motion, being able to find the velocity at any point on a rigid body, and being able to find the acceleration at any point on a rigid body, including the center of gravity, because Newton's law said F is equal to ma, where a is the acceleration of the center of gravity. So we're going to go around these rigid bodies to be able to find, you know, the acceleration at the center of gravity in order for us to be able to talk in Newton's law. Okay, guys, so on the exam, I'm going to update this, and I'm also going to update this, right, the 12.4, just to make sure that this answer was provided for you, so that won't change anything. Your grade will automatically be updated, all right, to the test problems that you were given.